So, alright, you are welcome to this week's class on photoelectric effects. Firstly, what is photoelectric effect? So, when electromagnetic radiation of high enough frequency is incident on some metal or the surface of a metal, so electrons are emitted. Electrons are emitted. So, photoelectric effect that phenomenon is called photoelectric effect. So let me explain using this diagram. So when you have light, so let me use red. When you have light, this light, okay, hitting this metal, so this is the metal surface, the surface of the metal, so electrons are emitted under certain conditions. What are the conditions? Number one, the energy of this light, okay, of this incoming light is high enough. What do we mean by high enough? Number one, the energy of the incoming light must be more than the work function of this metal. What is work function? So the work function is the minimum energy that is required to liberate electrons, or to liberate an electron from the surface of the metal, So that is work function. So this work function, let me denote it as W. It is related to another term that we call threshold frequency. So this work function is like energy. So the energy of the incoming light must be more than the energy that is required to remove the electron from the surface of this metal. Okay, so that work function is a Planck's constant H multiplied by the threshold frequency. So here W is the work function, H is Planck's constant. You are familiar with this Planck's constant. We used it in our last class. And this nu is so let me use nu naught because it's the threshold frequency. So nu naught is the threshold frequency. So this energy is related to that's the work function is related to the threshold frequency. So let me explain again. The work function is the minimum energy that you require to liberate electron from the surface of a metal. And photoelectric effect is concerned with liberating electron from the surface of metal when light of sufficient energy is incident on the surface of that metal. So the incoming light must be more than this work function. So the incoming light, that is this incoming light, must be must be greater than the work function of the metal before electrons are liberated. Okay, so it must be more than this, it must be greater than the work function. So, and I believe you know what the work function is now. So, and I said the work function is related to the threshold frequency. So let me call this equation 1. Okay, so the threshold frequency, what is the threshold frequency? It is the minimum frequency that is required to liberate an electron from the surface of a metal. Okay, so the work function is related to this threshold frequency via this equation 1. Alright, so what we actually mean is that if you have a metal, so let's say you have a metal surface and there is an electron here. So this is an electron. So let me draw E, an electron. And you shine lights of enough energy, so let's say the energy, and that energy is greater than the work function of the emitter. So what will happen is that the electron will be emitted. The electron will absorb photon. So what we are after is we want to remove that electron from the metal because there are electrons at the surface of the metal, so we want to remove them using light. That's what we call photoelectric. Okay, so generating electrons from light. So the electrons that are at the surface of the metal will absorb the energy of the incoming photon. That's the electromagnetic radiation. So it will absorb it, then it will now have enough energy. So that enough energy is the work function, which is the minimum energy that is required to liberate the electron from the surface of the metal. Now, if these electrons are emitted, they will have kinetic energy. We said that the energy of the incoming photon must be greater than the work function. So the remaining energy, okay, because it's like E minus W is positive. So the remaining energy will be used as kinetic energy by the photoelectrons. Okay, so what are the photoelectrons? So the photoelectrons are the electrons that are liberated in a photoelectric effect experiment. So photoelectrons, so are the electrons released or liberated in a photoelectric effect experiment. So, all right, so we have defined some terms now. The first term that we defined was photoelectric effect. So we said when electromagnetic radiation of high enough frequency is incident on a metal surface, that electrons are emitted from the surface. The second term we defined was work function. We said is the minimum energy required to liberate an electron from the surface of a metal. So, and the third term is threshold frequency. We said is the minimum frequency that is required to liberate electrons from the surface of a metal. And the last term that we defined is photoelectrons. So I said they are the electrons that are released or liberated or emitted in a photoelectric effect experiment. All right. So we said that the energy of the incoming photon, that is the photon that strikes the electron, okay, that is, so the electron absorbs that photon. We said, okay, let me label this as equation 2. So from this equation 2, we can write that E equals the work function plus the kinetic energy, or the maximum kinetic energy of the photoelectron. So this equation and equation 2, they are actually the same. Now we have defined what work function is. We said work function is h nu. That's equation 1. H is Planck's constant and nu is the frequency. In our last class, we wrote the formula for calculating the energy of a photon. We wrote it as h nu. So h is still the Planck's constant and this nu is the frequency of the incoming photon. That is the incoming electromagnetic radiation, okay, that strikes the surface of the metal. So it means we can write this equation as h nu equals h nu naught plus the maximum kinetic energy of the photoelectron. So this Ke is the maximum kinetic energy of the photoelectrons. Okay. Now, if the electrons are liberated, the light is more than, that's the energy of the incoming light is more than the work function, and it strikes the cathode, and electrons are liberated as called photoelectrons, and we reverse the polarity of the battery. We want to stop, so the photoelectrons are already in motion, they have kinetic energy, okay, the kinetic energy using this equation 2. Now we want to stop the kinetic energy. What we do is to vary this voltage. We use this to vary the voltage. This is a rheostat. So we use it to vary the voltage. So it will get to a certain point that no electrons, that's the current of the photoelectron, would not turn to 0. So there will be no electron, no current again, no photocurrent. So it will get to that point. So when it gets to that point, so we say that the stopping potential, that is the potential that we need to stop the photoelectron. Okay, so if you want to stop, so the photoelectrons are already in motion. Now if you want to stop them, you reverse the direction of the battery and you vary this rheostat so that till you get to a point whereby no current is recorded by this ammeter. No current is recorded, no current is flowing again. So that voltage, we call it the stopping potential. The stopping, so let me write it, stopping potential. So let me denote it as Vs, stopping potential. So if we multiply this voltage by the electronic charge, okay, of course we get energy. So this energy is the maximum kinetic energy of the photoelectron. So the stopping potential, that the potential that you need to stop the photoelectrons, okay, so it's equivalent to the maximum kinetic energy of the photoelectron. So let me call this equation 3 and let me call this equation 4. So please keep these equations. So equation, we can say this is equation 2 star or 2b. Okay, so the energy of the incoming photon equals the work function plus the maximum kinetic energy, or you can write it as h nu, that's the Planck's constant multiplied by the frequency, equals the work function. The work function is Planck's constant multiplied by the threshold frequency plus the maximum kinetic energy of the photoelectrons. Alright, so let's take some examples. Alright, so let's take this example. The work function of a photosensitive surface is 3.2 electron volts. Will photo emission occur if a photon of energy 3.8 electron volts is incident on the surface? So that's the first part of the question. So are we going to have electrons that will be liberated if the work function of the surface is 3.2? If the work function of the surface is 3.2 electron volts and the energy of the photon is so this is the work function and this is the energy, so this is the energy of the photon. So the work function, so work function equals 3.2 electron volts, and the energy of the incoming photon is 3.8 electron volts. What did we say our condition was? We said that the energy of the incoming photon, this must be greater than the work function. Okay, so here we have 3.8 electron volts as the energy of the photon, and we said it must be greater than the work function, which is 3.2 electron volts. So this is true. So 3.8 is greater than 3.2 electron volt. So since the energy of the photon, which is 3.8 electron volts, is greater than the work function, which is 3.2 electron volts, therefore photo emission will occur. Photo emission will occur because the energy of the incoming photon is greater than the work function. Let's say the question says that the energy of the work function is 3.2 and the energy of the incoming photon is 3.0. In that case, 3.0 is less than 3.2, so no photo emission will occur, no electrons will be liberated. Now the second part says if yes, because now the answer is yes, that photo emission will occur. Find in joules the maximum kinetic energy of the photoelectron. So what do we use? We use equation 2. We use equation 2. That what is equation 2? Equation 2 is that the energy of the incoming photon minus the work function equals the maximum kinetic energy. Okay, so and we said E is 3.8 electron volts minus 3.2 electron volts. So 3.8 minus 3.2. So let's take our calculator and do 3.8 minus 3.2. So what do we get? So obtain 0.6. So obtain 0.6 electron volts. Okay, so we can say that the maximum kinetic energy, so therefore the maximum kinetic energy of the photoelectron is going to be 0.6 electron volt. But the question asks us to calculate the energy in joules. The question says, if yes, find in joules. Look at it. In joules. So we have to convert this electron volt to joules. Thank God we are given the hint. We are told that 1 electron volt is 1.602 times 10 per minus 19 joules. So 1 electron volt equals 1.602 times 10 per minus 19. So 0.6 electron volt will be 0.6 times 1.602 times 10 per minus 19 joules. Okay, so joules. So in that case, what will be the answer? So 0.6, so 0.6 multiplied by 1.602 times 10 per minus 19. So in that case, we obtain 9.612 times 10 per minus 20. So 9.612 times 10 per minus 20 joules. So that is the maximum kinetic energy. So maximum kinetic energy of the photoelectrons in joules. Okay, so that solves that. All right, so example 2. Light of wavelength 400 nanometers. So we are given the wavelength of the incoming light as 400 nanometers. So it's incident upon lithium, which is a metal, and the work function of lithium is 2.93 electron volt. So we can say work function, okay, is 2.93 electron volts. So the wavelength of the incoming photon is 400 nanometers. So the first question says calculate the photon energy. So A, how do you calculate photon energy? We have done that in our first class, in our last class. So E equals H nu. Okay, the energy incoming photon, the Planck's constant multiplied by the frequency. But in this case, we are given the wavelength. Of course, we used in our last class hc over lambda. So c over lambda is frequency. So c is the speed of light and lambda is the wavelength. So nu, which is the frequency, is c over lambda. Nu is c over lambda, or c equals lambda multiplied by nu. So this is a well-known formula. This is a well-known formula. Okay, so in that case, the energy will be H. We are given H to be 6.626 times 10 per minus 34 joule second, multiplied by C, which is speed of light. We are given as 2.998 times 10 per 8 meters per second, then divided by wavelength, and the wavelength is given as 400 nanometers. So in our last class, we learned how to convert from nanometer to meter. Can you remember? So 1 nanometer is 1 times, so 1 nanometer is 1 times 10 per minus 9 meters. So in this case, 400 nanometers is 400 times 10 per minus 9 meters. So if we take out our calculator and do this, so let's take out our calculator and do this. Okay, so let's say the numerator is 6.626 times 10 raised to power minus 34, times 10 raised to power minus 34, then multiplied by 2.998 times 10 raised to power 8, then divided by the denominator, which is 400 times 10 raised to power minus 9. So what do we have? Okay, so we have 4.966 times 10 raised to power minus 19. So 4.966. So 4.966 times 10 raised to power minus 19 joules. Why joules? So this second will cancel this per second, second will cancel per second, then this meter will cancel this meter. So you'll be left with joules. Okay, now that is the A part. Okay, so the A part says calculate the photon energy. So the photon energy is 4.966 times 10 per minus 19 joules. Now the second part of the question says that we should calculate the stopping potential. The stopping potential. Now we know that the stopping potential is related to the maximum kinetic energy of the photoelectrons. I think we gave this formula in equation equation 4. Okay, the stopping potential is related to the maximum kinetic energy. So, and the maximum kinetic energy can be obtained using equation 2. So we use equation 2 to obtain the maximum kinetic energy, so which is the energy of the incoming photon minus the work function of the matter, minus the work function of the matter. Okay, so now what is the work function of the matter? The work function of the matter is 2.93 electron volts. Okay, and the energy of the incoming photon is this 4.966 joules times 10 to the minus 19 joules. Now you cannot just subtract joules from electron volts, so you must put them on the same unit. They must be, so the energy, the unit of energy must be the same as the unit of this work function. So is either you convert these joules to electron volts, or you convert this electron volts to joules, so that they'll be in the same unit. So that is when you can find the difference between the two. So let's convert this energy to electron volts. So the energy, so the work function is 2.93 electron volts, while the energy is 4.966 times 10 to the power minus 19 joules. So we need to convert this joules to electron volts. Now recall that 1 electron volt is 1.602 times 10 to the power minus 19 joules. So it means if you want to convert these joules to electron volts, we have to divide by 1.602 times 10 to the power minus 19 joules. So let's go back to our calculator and we say divided by 1.602 times 10 raised to the power minus 19. Sorry, 1.602 times 10 raised to the power minus 19. So that we obtain 3.09999. So that's approximately 3.1. So that we obtain the energy to be 3.1 approximately electron volts. So therefore the stopping potential, the energy EVS, which is the maximum kinetic energy, is E minus W, work function. So the E is 3.10 electron volts and the work function is 2.93 electron volts. So 3.1 minus 2.93, 3.1 minus 2.93. So that will give us 0.17. So that's this EVS equals 0.17 electron volts. So, but we have to calculate the stopping potential. You just divide by E. You just remove the E, the electron volts, so that you have only Vs, which equals 0.17 volts. So this is the stopping potential. So it means this is the potential that you have to stopping potential. This is the potential that you have to apply to stop the movement of the photoelectrons. So this solves the problem. So this is the end of the photoelectric effects class. Okay, thank you. See you some other time.